Hey, AP Pre-Calc community, this is Miss Adams from Flamingo Math. Today we're looking at the tangent function in the first lesson. Remember that we know the tangent function matches the measure of an angle in standard position with the ratio of tangent being sine divided by cosine, provided cosine isn't zero. We also know that this is the slope of the terminal ray of theta. The tangent curve is going to be the graph of the tangent function, and the tangent of theta is the ratio of the change in the y values to the change in the x values between any 2 points on the ray. That's what we know as slope. Let's look at example 1. We have the graph of the tangent function. We'll complete one full cycle in the interval from 0 to pi. So the period of tangent is going to be pi. However, there's a vertical asymptote at pi over 2, so we know this does not exist. We want to know on what continuous interval can the entire behavior of the function be shown. So first we're going to complete the table of values based on our unit circle that we learned earlier in this chapter. So completing that table, we want to state the intervals of x where the y values are increasing. That occurs from 0 to pi over 2. Does not include pi over 2 because we have that vertical asymptote. And it also happens on the other side from pi over 2 all the way up to pi. For part C, state the intervals of x where the y values are decreasing. In this case, you see the y values never decrease. We say that the function is monotonic and it's increasing on its domain. Monotonic means it has the same behavior overall. Example 2, we want to graph the graph of the tangent function, and on what continuous interval can the entire behavior of the function be shown. Well, if we have an asymptote at pi over 2, then every pi radians we have another complete cycle. That would put another vertical asymptote at 3 pi over 2, another one going to the left at negative pi over 2, and negative 3 pi over 2. So the function is monotonic and increasing over its domain. It looks like this. That gives us the interval from negative pi over 2 to positive pi over 2 for our values of theta. Actually, we should use theta, not x here. This would also change our label on the x-axis. This should be theta because we got our argument is theta and our y-axis is y. Then completing these, we've got another complete cycle there. We have another complete cycle here. And then some little half cycles in between here and here. In part B, find the points of inflection. Well, they're going to occur every pi radian. Points of inflection. That would be here, 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 here. So those would happen where x is 0 plus pi times k, where k belongs to the set of integers. Let's look at the characteristics next. The domain of tangent is going to be b, where the argument bx is not pi over 2 plus every pi k intervals, where k is an integer. And the range is all reals. The x-intercepts are every pi k. 0, where k is an integer. The y-intercept is at the origin. We have odd symmetry, which means it's origin symmetry, and we have an asymptote at every pi over 2 plus pi k radians, where k is an integer. And believe it or not, we do have 5 key points again. Those key points are an asymptote to start with. That's the first one. And then we have a low point. I'll show you what I mean by that. Then we have an intercept. And then a high point. And then finally an asymptote. So it's still 5 key points to graph the function. And if you go back and look with me, I can show you what I mean by that on the graph. So here I have the first asymptote, that's our first key point, then a low point, and then an intercept point, and then a high point, and then an asymptote. So if you know the first asymptote and the last asymptote, halfway between is the intercept, and then a quarter of the way, so halfway between the asymptote and the intercept is a low point, provided your amplitude is 1, and then halfway between the intercept and the asymptote is a high point, provided the amplitude is positive 1. In example 3, we're going to take a look at what happens when we have negative in front of our x. The amplitude is going to change. And we know that pi over the b value is the period. So we have a period of 1. Our a is negative 1 here, and that's going to cause the parent function to be reflected across the y-axis. Causes our parent tangent of x to reflect across y. So what's going to happen to our asymptotes? They're still at negative pi over 2 and positive pi over 2. So we know the beginning and the end. We know in the middle is an intercept, but the negative 1 on our a value is going to cause the low point to be a high point and the high point to be a low point. So our graph is going to go decreasing from left to right, because we know y is negative 1, that's my a, times the tangent of 1x. This is our b value, and this is our a value. And we can draw several of those repetitions on the graph paper that they've given us. So our function is decreasing from left to right. It's monotonic, which means the behavior's the same, and it's decreasing. So we can say y is decreasing on its domain. Let's graph some variations of the tangent of bx here. Find 2 consecutive asymptotes by setting the argument equal to the parent asymptote is one way to transform a function. That's a tangent curve. Then we can identify the x-intercept that's midway between, and then we can find the points for 1/4 and 3/4 of the way between the consecutive asymptotes. And those points will have y-coordinates of negative a and positive a. And then we can graph additional cycles from the left to the right as we need based on our direction. So this is a great set of instructions for what we want to do. And just to refresh our mind about the key properties for the tangent function, the domain is bx plus c, can't be 0. The a value is our vertical dilation. It's a stretch factor or a shrink factor depending on the size of the a value. We have an asymptote. We have a negative a a 0, we have a positive A, and another asymptote for our key points. The range is negative infinity to infinity, and the period is pi over b. So let's give this a try for example 4. We want to use transformations, graph each function, state the period, and show all the asymptotes. In this first one, we want to graph negative tan of x over 2. So we have an a value of negative 1. We have our argument 1/2 x has to be equal to the left asymptote, which was negative pi over 2. So that puts our left asymptote at negative pi. And if we want to know the right asymptote, we just set that same argument equal to positive pi over 2, where 1/2 x is positive pi over 2. So the right asymptote is at pi. And that graph would look like, here's my rough sketch. I know you have graph paper on your paper, but you notice that we have the point at 0, 0. That's halfway between the two asymptotes. We have a point here at negative pi over 2, 1, and we have another a value here at positive pi over 2, negative 1. So this is 1, and this is 1 here. And this is pi negative and pi positive. And then finally, for example 4b, we know that the a value is 1. We have our argument pi over 4x is set equal to negative pi over 2. Solving that for x is going to give us x is negative 2. Doing the same thing for our right asymptote, which the parent right asymptote is at pi over 2. Solving for x, we see an asymptote at positive 2. And our scale is going to be different than example 4a. 4a had the x-axis in radian measure, but here on example 4b, our x-axis is going to be in numeric values 1, 2, 3, and so on, 1, 2, 3. We have a vertical asymptote at negative 2. That's our first key point for here. We have a vertical asymptote at positive 2. This is 2 and negative 2. Then halfway in between is an intercept. Halfway between the first asymptote and the intercept, we have a low point at negative 1. So this is negative 1, negative 1. Halfway between this intercept and the asymptote, we have a high point at 1, which is 1, 1. And our graph is increasing on its domain from left to right. And the period is 4. Not radians, just 4. Thanks for joining me today. I'll see you next time.